Hello everyone, welcome to lecture 18 of this course. In the previous lecture we discussed the principal type algorithm. Today we are going to discuss the Curry-Howard correspondence and the intuitionistic implicational logic. Curry-Howard correspondence is a very deep and fundamental result in lambda calculus. So we first study the context before Curry-Howard. So in the early 20th century, logic and computation were seen as separate domains. When we study logic, it essentially consists of proofs, propositions and truth. Computation on the other hand, we essentially talk about functions, programs and their execution. Haskell Curry and William Howard and others noticed deep structural similarities between proofs in logic and programs in computation. So for example, Curry in 1934 noticed a connection between the types of combinators, a form of computation, and axiomatic systems for intuitionistic implicational logic. This was in 1934. Now in 1969, William Howard developed the concept further by observing a direct link between proofs in natural deduction, which is a type of proof system, and terms in the lambda calculus. He demonstrated how a formal system of proofs, a logical argument, could be represented as a program in a computational language, leading to the idea of propositions as types. So we have seen types, so then it is related to propositions in logic. So the key motivation was to explain why certain formal systems of logic look almost identical to formal systems of computation. So proofs resemble programs. A proof of a logical proposition is like a program. The steps in a proof correspond to function applications, that is the computations. The propositions resemble types. So we have seen types, that means the logical formula corresponds to a type. So if we have a logical implication like A implies B, where A and B are propositions A, this arrow then denotes implication. So in a logical context it is A implies B. That arrow represents implication, logical implication. Now this behaves just like function type, which is A or B are types, and it is a mapping from type A to type B. So the behaviors and the structures they are same. So that is how we say propositions resemble types. This is the first observation, and that is the key foundation point from which this correspondence lies. That was observed by Howard. So now we give some intuitive examples. We have seen modus ponens. Modus ponens is appearing in different variants and different places. So in modus ponens in logic we like this is a notation we have already seen, that A and A arrow B. So we write this is B. This is modus ponens. The structure is written in this way. So we say from A and B we infer B. So you see here with these red colors that we have marked, it is for saying that A and B here, these red colored letters, they are standing for propositions here. When we talk about logic, we mean these letters denote propositions. When we talk about programming, so we say if a function takes as input an argument of type A and returns another argument of type B, so the function type is A arrow B, and if x has type A, then the fx will be of type B. Now AB, the role of AB changes to types, but the structure hasn't changed. The structure that from A and A arrow B infer B, so here also type A and type A arrow B infer B, that structure remains same. Then we move on to type theory, and we have seen one instance in arrow E, that means elimination of this arrow in lambda calculus, in TL lambda. In TL lambda we have in the context gamma, if F has type A arrow B, so again this type, and in the context gamma x has type A, then arrow E says that in the context gamma fx has type B. So we have found that in different fields this modus ponens is appearing in different form, but the interpretations are different for these letters. One is that it is a proposition. So we have two things, one is a proposition and we are viewing it then as a type, or types if we have started with, we now view it as a proposition. Furthermore, normalization and cut elimination. In logic, cut elimination means we are simplifying proofs or we are removing detours in a proof. This is exactly what we do in beta reduction in lambda calculus with simplifying function applications. Next, for the foundations of programming languages, understanding this correspondence gave a way to design type programming languages like Haskell, ML, Coq, where writing a program is the same as proving a theorem. Now, the significance of this correspondence is that it unified logic and computation under one principle. It showed that programming could be guided by mathematical logic, and later on it was also advocated that programming is a mathematical activity by Edgar Dijkstra in a different context. Although it gave birth to type theory, which is the basis of modern programming language semantics. It led to the development of proof assistants like Coq, Agda and Lean. It led to functional programming as logic in disguise. So thus we see now that programming is in essence we are doing some logical deduction. So more about it we are going to discuss. So for the Curry-Harvard correspondence, so we have seen the types and propositions, they correspond. So for the logic we are considering intuitionistic implicational logic for giving the idea of this correspondence. So intuitionistic implication logic can be viewed as a fragment of propositional logic. So in propositional logic the operators are and, or, negation, implication, and in intuitionist logic we have only one operator, that is implication. Other operators are not allowed here. And atomic propositions, we know propositions that have no internal structure. So if P and Q, for example, they are atomic propositions, then PROQ will be a composite formula. Now we know that this PROQ, the truth of PROQ is that PROQ, P implies Q is false when P is true and Q is false. Otherwise it is true. So examples of this structure, we have seen several examples of this, so we just present here. So for instance, when we said that if a lambda I term has a normal form, then all its subterms have a normal form as well. So the P part is this one and Q part, so P implies Q, this is true. And then if we have a say, if a number is prime, then 2 is then it is odd. So this we know it is false. So P is true and Q is false. So then this truth value is false. But from now on we are not going to use the truth table interpretation of P implies Q. Rather we will consider provability of P implies Q using some rules. So intuitionistic implicational logic, we are going to have IIL. So the grammar for this sentences that we are going to get is A is a proposition, the proposition is a formula, and if sigma and tau they are formulas, then sigma tau is also a formula in this logic. Now if you view A as a type and arrow this is implication as a function, then sigma is the type language of TL lambda. Now here let us view A as a type, that means it is a type variable. In our previous discussion we said it is a type variable, and this arrow now is a function type. Now this corresponds to the type language of TL lambda. We call the type language of TL lambda a type variable is a type, and if sigma and tau are types, then sigma is also a type. And this is the language L2 that we said L1, L2, L3, and this is the weak polymorphic language because it has no for all quantifiers. So now you see the structure of the formulas that are coming in this logical language is the same as the structure of the type language that we had. The difference being that here when we are talking about logical formulas, we are interpreting this arrow as implication, logical implication. On the other hand, this arrow was interpreted as a function type, is a function from one type to the other. Now this logic is used for the study because intuitionist logic, not classical logic, is the foundation of many polymorphic type theories. So we are going to use IIL to develop the Curry-Harvard correspondence. So first we will study this logic, intuitionistic implication logic, and then we take on the Curry-Harvard correspondence. So the first example in this is called implication. So in logic we write this, say A implies B implies A. So this means assume A, then given B we can still conclude A. So if you think of it as type, it is a function taking input of type A and returning a function of type B arrow A. If we move on to lambda, we can write a lambda expression like lambda x has type A, lambda y has type B, and the body is x. So, this is actually the function first, that means taking two arguments and returning the first argument. So, the m here, the lambda term is the first, that is lambda x dot lambda y dot x, and the type is A arrow B arrow A, that is m has type tau. So, that means this lambda expression is a type lambda expression, it connects one untyped lambda term and a type, and we say m has type 2. This m has type 2 has connected these two different things. One is a type and that is coming from some type language, and then this m has type tau. These two are connected, and then this connection is actually the what we are developing, that now we are viewing tau as a proposition in a logic, and then we are trying to understand how this deduction of m has type tau is the same as the deduction of tau in the logic. Now, type tau in programming corresponds to a logical proposition tau. A program or a term m of type tau corresponds to a proof of the proposition tau. That is, there are two parts here. From a deduction of, say, if we are in the system T A lambda, then in the T A lambda, if you have a deduction of m has type tau, we can obtain the proof of the proposition tau in IIL. That is called lambda to logic. This is part 1. And the part 2 is, from a proof of the proposition tau in the logic, we can obtain a deduction that a term m, that has type tau in T A lambda. So, that is logic to lambda. So, here we emphasize on this can obtain means. That means suppose I do perform a deduction of this m has type tau in T A lambda, and I do carry out a deduction of this proposition tau. I will find that these two structures are identical. But when we say can obtain means, from the deduction of m as type tau in T A lambda, this deduction we can make some syntactical changes, not structural changes, and we can obtain the proof of tau in T A lambda. That means we need not carry out the deduction separately, we can obtain that proof from this deduction. In the same way, from the proof of the proposition tau in the logic, by carrying out some syntactical changes not on the structure, we can obtain that there is a lambda term m that has type tau in T A lambda. This is what the idea of Curry-Harvard correspondence. And we are now restricting attention to the logic IIL. Okay, now we discuss the deduction rules in IIL. So, first we have axioms or the assumptions. If A is assumed, then we can conclude A. Next, it is the arrow I that is introducing the arrow. If using A, we can derive B, then we can conclude A arrow B. That A arrow, again when I say arrow, it means in the logic context it will be implication, and in the type context it will be a function. Now, arrow E is that eliminating the arrow, from A implies B and A, we can conclude B. So, these are the three rules, and essentially two in the, if we consider arrow I and arrow E, and this corresponds to that rules that we had in T A lambda. So, these rules can be presented in the way that we discussed earlier, that arrow E is, we have a numerator denominator structure, and we have sigma implies tau. From sigma implies tau and sigma we can infer tau. This is the standard way of representing. And arrow I now it is a little bit different in logic. So, here we write in this way. So, we start with this. This means we are assuming sigma. So we put this in square bracket, assuming sigma. Dot dot means that we perform some steps of derivation and we come up with tau. That means assuming sigma, we have arrived at tau, and then we can say sigma logically implies tau. After this line we can say now we can conclude assuming sigma and tau. Now because now we are inferring this, now this sigma is discharged. This is how arrow I rules we have to write discharging sigma. This is the idea of the structure. So furthermore we can go a little bit more deeper. We can say this meaning is assume a proposition say sigma. Then after some steps, these are given by dot dot, that means by one step, two step, several steps, we derive tau. This argument demonstrate that sigma logically implies tau. So when you are moving from tau to sigma arrow tau, that means we are moving from here to here, this assumption of sigma is discharged. This is the interpretation of this. For a detailed discussion on this, we refer to chapter 4 of John Mitchell's Foundation of Programming Languages. Now remember we discussed cut elimination, that means simplifying a proof. Now cut means in a proof is, so this is the standard, assuming sigma, some steps we have added a tau. Then when we are moving from tau to sigma logically implies tau, we discharge sigma. This is one deduction. Now there is another deduction where this dot dot, this could be another deduction. So this is another deduction, say 2, this is another one deduction 1. We have deduced sigma. Now we are doing arrow E. So here arrow E is done. Now this arrow is after doing this arrow, that means by discharge, we then do arrow E. That means this arrow is eliminated and we obtain tau here. This is called a cut in the logical deduction context. So cut elimination means we are eliminating this these steps and we are obtaining say sigma we have obtained using deduction 2. This sigma we obtained using deduction 2. So here we had deduction 2, we arrived at sigma. Now these steps we are now using to arrive at tau. We are arriving tau. Then there is no need to go to these steps. So this is called cut elimination, that is called simplifying proofs. So now we will consider some examples of proofs in intuitionistic implicational logic. So the first example is you have to give a proof of A implies B. This whole thing implies A, this implies B. So steps, first we assume A implies B, then we assume A, then we do arrow E. So that means from 1 and 2, so from 1 and 2 we can derive B. Given A arrow B and A, we can derive B. Now we have obtained B using by assuming A, so we can discharge 2 and we can write A implies B. Now we have arrived at A arrow B by assuming A arrow B. So we can discharge 1 and we can say A arrow B implies, this term implies A arrow B. So this is the proof. Now we have to present it in the structure of arrow E and arrow I, that notation. So what we had, we are assumed A arrow B and we assume. So we put it in these square brackets, arrow A and arrow E. Then we applied arrow E. So we obtained B. Then we are discharging A. So we have obtained from A, we have obtained B. So we can say A implies B. Now assuming A arrow B, we have obtained A arrow this part. Then we are discharging this and we are writing A arrow B arrow. Now here when we are writing this, we are writing this star star and star. So these are the positions that we are marking here. So instead of star star we can write something else as well. So if you recall, so when we discussed construction tree of a term or a type, so we had labels. So remember that if M is a term and these are the position levels, say we had 2, so we had a position level, say 2 numerical numbers we are there. So we had a number here, sequence of from 0, 1, 2 we had a this. So we can also write it. So this is the same thing as the construction tree of a term or type. So we can do the position of this tree and we will have say this is 1, 2, 3. So it will be of length 3, we can have some involving 0 and 1, 2. So we are just using star for reference. It is not so important to use that. So we could have done other symbols as well. It hardly matters. So now the interesting part is, so we have a type and we have shown that this type, it is a logical formula. So that we have given a proof of the logical formula using the rules. So now the logical formula we can view it as a type. If this be the type and we know that this is the lambda term, So we are now associating one lambda term with this type, viewing this logical formula as a type, and we have already studied several lambda terms. So this corresponds to the lambda term. This is the apply function lambda f dot lambda x dot fx. This term has type this. So now we are trying to intuitively understand the correlation between this m has type tau, and then the tau is viewed as a formula, and these two things we are trying to get some understanding. So we have a term here, this is the lambda term, and now what we do, take the formula, view it as a type, and now associate some lambda term. So this is what we have, this is the apply function. So now we consider the second example. Now there what we have a arrow b, a logically implies b, this logically implies b, b implies c, this implies a, and this implies c. We have to give a proof of this in IIL. So we first assume a implies b, then we assume b implies c, then we assume a. Now these are the three assumptions that we make here, first three lines. Now 1 and 3 we get b, 1 and 3 we are getting b. From 2 and 4 we are getting c. Now discharge 3, that means a we can discharge. So we will get a implies c. So a implies c we have obtained. Now we can discharge b implies c. So we will get b implies c, this whole thing implies a implies c. Now we can discharge 1. So we will get this given logical formula. This we have obtained. Now we will present it in that style of arrow E and arrow I. So we have assumed A arrow B and A, and we have obtained B. We have assumed B arrow C, B implies C. So B implies C, we get arrow E. If we do now again arrow E, we get C. Now we have assumed A and we have obtained C. So we can discharge A. So discharging A at this point. So we get A arrow C. Now we have assumed B arrow C to infer this. We have got this point from B arrow C. So we can say B implies C implies A implies C. That is discharging B implies C at this point. Now we have also have this assumption A implies B. So now we discharge A implies B at this. So we get this. So this is the proof of this given formula. Now as before, we can view this formula as a type. So then the lambda term corresponding to this is well known, we know it is the composition function, lambda f, lambda g, lambda x, g of fx. That means if I do f here, f is of type A arrow B, f is of type A arrow B, and x is of type A, so return type will be B. G has type B arrow C, it is taking B giving C, so we are getting C. So in the next example also we have seen that we took a formula in the logic, we have give a derivation of the formula. Now we are interpreting this formula as a type, and we are saying, look, this is the lambda term corresponding to this type. So now we present the third example. So this example is the formula is A implies B implies C. This is one first part. This whole thing implies A implies B, and this implies A implies C. Now first we assume A implies B implies C. Then we assume A. Combining these two, 1 and 2, we derive B implies C. Now we assume A implies B. From 4 and 2 we get B, derive B. Now we have B arrow C and B. So that means from 3 and 5 we derive C. Now discharge 2, that means assumed A, that means we can get A arrow C. A arrow C part we obtained. Now we assumed A arrow B, that means we are discharging this. So we will get A implies B implies A arrow C. Now we discharge 1, so we arrive at the given formula, and this is the proof. And now we just translate it in this notation, and we write here. See here we assume A arrow B, A implies B implies C, and we are assuming A, we are applying arrow E. So we get B arrow C. We also assume this part, A implies B and A. So we get B here. Again arrow E is applied. Now again arrow is applied. to B and B arrow C. Actually, we have to write this should be this way, and there we have to write, we should write this way. This is one. So arrow E, then we get C. Now assuming A, so we discharge A at both the places. All the assumptions of A we are discharging. Discharge A at both the places. So we get A arrow, A implies C. Now we discharge A implies B at this point. So we get by arrow I again we get this A implies B implies A implies C. Again we apply arrow I, so we discharge this at this point and we derive it, come at this one. So this is the proof of the given formula. Yeah, so we have seen this proof in IIL. Now if you take the formula and view it as a type, so this will be the type. Now we are asking whether there is any lambda term corresponding to this type. So recall we have studied one combinator, S combinator, when we studied SKI, and this combinator is like f lambda g lambda x fx gx. This term has type 2. Why it is so? Now this is g of x is b, f of x is b ROC. B ROC applied to b will be c. So this term has this type. So all these examples, 3 examples that we have studied, first we have understood how to give a proof in IIL. Then we also have shown that now we are going to view this formula as a type. If that be the case, then we are asking whether we have a term, lambda term that has this type. And indeed for all these examples we have found there is a lambda term that has type. So this is intuitively giving us some correspondence between types and formulas and lambda terms, how these proof structures are linked. This intuitively we are getting some ideas. Okay, now we consider another formula. So this is a formula like A implies B. This whole thing is implies, assuming that A implies B, then this implies A. This whole thing implies A. This is the formula in IIL. Now this is called Peirce's law. Now this formula is a tautology in propositional logic. However, this formula is not provable in IIL. So we first see what intuitively why this formula is a tautology. So we make this as the inner part, this is the outer thing. We call this, where inner means this part, outer, and in this the entire formula. So let us assign all the truth table assignment we want to do, and let's see whether it is indeed a tautology. If A is true and B is true, then this part is true. This is true, A is true. So true implies true, this is true. Now A is true, B is false. That means inner part is false. Inner part is false, outer false implies true, that part is true. False implies true is true. That 2 implies true is true. So this is also true. Now A is false and B is true. A is false and B is true, this part is true. B is false or true implies false, this is false. False implies false is true. So this is true. Again A is false, B is false. Now false implies false is true. Inner part is true. Now false implies true, true implies false, this is false. Now false implies false, this is true, so this is true. So all possible cases is true, so it is a tautology. However, if we now say, okay, this is a tautology in propositional logic, then in IIL, then this formula should be provable. However, this is not provable in IIL. This is the classic example that is illustrated when we talk about IIL to show that this is not provable in IIL. Now, it is difficult to give a direct proof in IIL. I mean, if you want to work out this the way we did, the strategy of that arrow I and arrow E, if you want to work with it, that structure will not work. And if you want to directly give a proof that it is not proven IIL, it is also quite difficult. So you are requested to give it a try. An alternate way of proving that this is not provable IIL is by the Curry-Harvard correspondence. So we summarize today's lecture. So we gave an idea about this Curry-Harvard correspondence, and for our discussion we consider intuitionistic implication logic, and we discussed how proofs or derivations are done in this logic. So the recommended articles are, so we refer to chapter 6 of Hindley's book, and we refer to chapter 4 of John Mitchell's book. So, we stop here. Thank you for your kind attention.